Well, hello everybody, welcome to the design of the Purlin. And finally we've done all the calculations of the load of the Purlin. Now we are ready to design the size of this Purlin here. The Purlin already has the size 2 by 3 inches wood, but we have to make sure that this Purlin is capable of carrying the load, especially the wind load. The wind load for this roof truss, the wood roof truss, the design wind load that I use here is 250 kilometers per hour. And the Purlin is sitting on top of the rafters 2 by 6 wood rafters. And we've done all this calculation right here. So to show you I'm just showing you the looks of the roof truss. This is the roof truss that we're designing. Now we start for designing the Purlin. Okay, here's our Purlin here sitting on top of 4 rafters. There are more Purlins in there on the roof, but you have to go for when you design, you have to look at the sizes of the Purlin, the length, especially the length. This is the commercial. You gotta look at the commercial length of the wood, and this is 3.6. So I use this 3.6. This is 12 feet long, and then that's why there's rafters there. Follow that dimension there, the length of 3.6, and you have to equally space them below the Purlin to carry the Purlin, and that's why it has 1.2 meter each. That's why there are 4 rafters there. So you gotta go for the commercial size of the wood when you design. We're going to design just one Purlin, and then calculate that load there, and then whatever we get there, the size of this, it's all applied to the entire roof. Alright? Excuse me. So the specification data for the type of wood that we use. This wood has the bending stress, allowable bending stress of 10.03 MPa, and the shear is the shear perpendicular to the grain. The grain goes horizontal, and that shear here, this shear, is perpendicular to that. It has very small shear. It's 0.76 MPa. Here's the size of the dimension of the Purlin, 2 inches by 3 inches. So I converted it to 50. Now this is actually 5. This is 5 centimeter for 2 inches. That's 5 centimeter, and 3 is 7.5 approximately. Okay, and during our calculation from the shear moment diagram with our Purlin, loaded Purlin, we found the maximum moment there is 0.464 kilonewton meter, and the shear is 1.545. So we're gonna use this information here, these values here, to design our Purlin now. And we have a centimeter here, and we have a kilonewton there. Therefore, we need to convert the MPa. MPa is Newton, 10 million Newton per meter square. So we got to convert that to kilonewton per centimeter square. So to convert that, okay, now first we have this formula here, 1, and formula 2. This is for the stress, this is for the shear. Stress is 6m divided by bd square, and the shear is Fb 3 times v. The v here is the shear moment diagram result, just 1.5 545 divided by 2 BD. So now let's go to the conversion of the allowable bending stress of this wood. It's 10.03 MPa. Now it's in Newton. Now you have to convert it in kilonewton, and it is in per square meter. We have to convert it to square centimeter. Alright, so therefore now let's start. The value of the 10.03 MPa is 10,030,000 Newton. And now we have to multiply it in a way to cancel meter square. So we have to put the meter square as the numerator so that it will be cancelled, but then over the centimeter right here below the meter. And question is what's the equivalent of 1 meter square equivalent to centimeter square? Okay, 1 meter has 100 centimeter, so therefore 100 times 100 for the square centimeter equivalent to meter square is equal to 100 times 100, and that gives you a 10,000 square centimeter. Now the meter there cancel, now centimeter left. Okay, now since this is in Newton, we have to convert it to kilonewton. So Newton here as numerator, you multiply it. First you gotta look at that way, which one you want to cancel and convert. Converting Newton, therefore Newton should be here as denominator, so it will be cancelled. So Newton here, and now, and 1 kilonewton as numerator. Now what is, how many kilonewton, how many newtons in 1 kilonewton? There are 1,000 newtons in 1 kilonewton. So that is the equation. Now goes Newton cancel, millimeter cancel. So what we have here is kilonewton and centimeter square. So now we have to calculate that, and calculate that. There are 6 plus 3, there are 9 zeros there, so therefore this MPa becomes in kilonewton 1.003 kilonewton per centimeter now square. Alright, so we have the MPa value now. So solve for the required section. Now what we're solving here now is the required section of the wood, of the purlin, due to the moment right here. See, we have to find the size of the purlin due to this moment here. See if it's capable of carrying that. What is the area? Okay, now therefore we have to use the formula 1 right here. F equals to 6m divided by b d square. The units in here in the BD square, this is centimeter and this is centimeter. It becomes, the unit becomes a cubic centimeter because this is centimeter as well. If you square this is a square centimeter. So the unit, don't be confused. This is cubic centimeter in result of this when you multiply this. Alright, so now let's plug this in here. The allowable, which is 1.003 kilonewton per square centimeter. Now substitute the value of the m, the moment there, from moment distribution, which is 4.64 kilonewton meter. Now we have to substitute that value here, and the f here will be substitute also the 1.003. So let's do that now in this formula here. So this is 464, and okay, now This is point 464 kilonewton meter, and the since this is in meter now, we're looking for centimeter. All right, so the meter will be converted to centimeter. To do that is to multiply this equation here by 1000. 100. I mean 100. There are 100 centimeter, 1 meter, so that meter they will become centimeter when you multiply 100 centimeter right here. And the allowable stress here is the denominator of this fraction there. There we go. And then now calculate this. 6 by multiplied by 4.64 multiplied by 100 divided by 1.03. The BD square now. So we're looking for the BD square there. This is from our formula here. We manipulate this formula. So in this formula here, we can solve for BD square by cross multiplying this. The F goes down here and the BD goes down there. That's why we have it here. Alright, this is the formation of our equation. Now we're looking for BD square. This is the section, cross section of the Purlin. So to calculate that now, and becomes the BD square now becomes multiplied by 100 divided by 1.003 becomes, it gives you 270.3. Okay, 270.3 centimeter cube. Okay, don't be confused with the cube. The reason why it's cube, as I explained, be here centimeter and this is centimeter square, so there's 270.3 centimeter cube. This is the section required, alright, to carry the moment, maximum moment from the shear moment diagram right here. So we calculated this. This is the required section. Okay, the BD square is the required here is 270.3 centimeter cube. This is due to the load. Okay, now because of the moment there, this is what we get. Now let's go to let's solve the actual. So we have that now. So and then we have the actual size of the Purlin, which is 5 centimeter by 7.5 centimeter. And now we gotta calculate this area here in cubic centimeter and then compare it to the required. Okay, this is the requirement. If we're less than this, if this section is less than this, then therefore this Purlin failed. Okay, it's not capable of carrying the moment there, the load. So now let's go for the actual BD due to the size of the Purlin right here. So that's the actual BD right here. Actual BD squared due to the size of the Purlin. The Purlin is 5 centimeter by 7.5 centimeter, and we substitute that BD square formula right here and solve this. 5 times 7.5 times 7.5, what we get here? Get 281.25 centimeter cube. Now the condition for safety is due to the bending moment of 4.64 kilonewton meter is the required BD square. It's the area section. The required should be less than the actual. This is the actual size that we use. Okay, so substitute the value there. The 270 right here, due to the load, 270.3 centimeter cube. Compare it to the actual. The actual is 281.25. Therefore, the required is less than the actual area dimension or cross section, we call it, as we call it, the dimension of the purlin, which is 2 by 3. So that's how you compare that safety. So therefore, since the required, this moment here, the load only requires 270.3 centimeter cube, but the actual capacity of the section here, the 2 by 3, 5 by 7.5, has capacity of carrying load capacity of 281 point. Section here is 281.25 centimeter cube, so it's bigger. Okay, bigger than this is larger than the required. So therefore, the purlin is safe, and follow that condition there of safety. And the purlin is safe in moment. Okay, that's safe for the moment, for now. And now let's check for the shear. Now the shear during our calculation, in the shear moment diagram, we have the maximum shear 1.545 kilonewton, and we have it here, and we have to use that to check our shear. So since the as well the allowable stress for the shear, this is the perpendicular shear, okay, transverse, is 76 MPa. You have to convert this again to the centimeter square. To do that, we gotta do that process again. This is 760,000 Newton. 760,000 Newton per meter square. Again, in 1 meter square has a 10,000. 10,000 centimeter square, and 1 kilonewton has a 1,000 Newton. And we solve it now. It will become, there are again 4 and 370. So this will become a point 0.076 kilonewton per centimeter square. Now, to solve for the capacity of the shear, so we have to use the formula number 2. FB is equal to 3V the shear and 2 times BD. So this is the shear, the actual shear. Okay, we have to solve for the actual shear of the capacity of the purlin. And now therefore we have to substitute the value of the shear right here. 1.545, that's kilonewton, and the size of our purlin is 5 centimeter by 7.5 centimeter. The actual shear capacity of the purlin. We are now shearing this purlin and apply this shear load of 1.545 kilonewton and see what happens. The shear now is multiplied by kilonewton. Go 3 times 1.545 divided by this 2 times 5 centimeter times 7.5, and this will give you zero 0.0168. 168. Okay, that's the actual shear due to the shear load of 1.545 kilonewton. The actual shear. Now let's compare the actual shear to the allowable shear for this type of wood. The allowable there is 0.076. Okay, that's the allowable. If this shear here due to the load exceeds 0.076, therefore the purlin is not capable of carrying the shear load of 1.545. So now compare this to the allowable. So 0.0168 and 0.76. Okay, what happened now? So as we compare here now, the actual is 0.016 kilonewton per centimeter square, and the allowable stress for the shear is 0.076. When this is bigger, then it's safe. So compare that is 0.0168 kilonewton per centimeter square is less than the allowable stress, which is 0.076. Okay, and since this is less than, therefore this size of purlin is capable of carrying the moment and carrying the shear load right there, and therefore the purlin is safe and adapt. Therefore we have to use the adapt 2 inches, which is 5 centimeter, and 3 inches. So adapt 2 by 3 inches purlin in terms of inches, and in terms of centimeter is 5 by 7.5 centimeter. Therefore the purlin is safe. Therefore this purlin here is safe to carry the calculated load that we have calculated, the load of the moment value 0.464 and the shear of 1.545. Alright, so that's the end of the design purlin. We found that this purlin is safe to carry the load, and the next will be the rafters right there, 4 of them. 4 of them in one shot of one purlin. Okay, we have to design it in a group. Alright, so that's the end of the video, and don't forget to subscribe, and thank you for watching. Bye bye.